Today, let me cover the ARM instruction execution. So, in the ARM microprocessors, in the architecture level, we need to understand how the instructions are executed and how the data processing is done, how the memory signaling is made. So, when you are accessing the instruction or when you're fetching the instruction, when you're executing the instruction. So, the in this today's lecture, we are going to see that. So that is something called as data processing instructions. So in during the data processing instructions, we have seen that there are two operands. So one of the operand is a register whenever you perform a data processing. So other operand can be a register or it can be an immediate data. So as I listed an example here, so if you see here, there is an example that I've listed. So now in this example, so we have used move r0 comma r1 as a instruction, r0 and r0 comma r2 as a instruction, and there is one more instruction which is actually an immediate addressing that I'm using, immediate addressing, which is move r1 comma hash 23451678. So this is a 16-bit data. As you can see, this is a 16-bit data, 32-bit data that I am loading here. Since ARM is a 32-bit core, so this value whatever I am loading is a 32-bit number. This is 32-bit. So there are four set of 8-bit data. Though this is actually the first 8-bit, this is the second 8-bit, third, and fourth. Each will be having 8 bits, so 8 into 4 32. So generally this r1 is a 32-bit register, so I need to load a 32. So we will see how the data processing is done for a register as well as for an immediate data. So the basic structure you know now, move r0 comma r2, move r1 comma, and there is, apart from that, there is one more. If you see, that looks like very a different way, like move r0 comma r0 and lsl 7. Sometimes it is even written as hash 7. Now see, move r0 comma r1. See, there is no meaning in moving the same byte, same value of the register r0 to r7 unless you have some special purpose or you wanted to do some operation like we do in C program. We make something called I++. So it is the same register will be incremented. So the same register will be modified in a different way. See, that's what the second operand in the architecture level. Whenever this kind of an addressing is done, whenever the data transfer is done, one of the operand is straight away taken. Okay, that's the first operand. Second operand is always goes through a shift register and then it will be moved for the processing. So the second operand is passed through a barrel shifter where it is subjected to a general shift operation, and then it is combined with the first operand in the ALU using the general ALU operation. It could be some data transfer arithmetic or it could be something else. So as you can see here, there is a requirement of a barrel shifter. This R0 value is now shifted. So why they are using, for example, let's say the R0 contains a value, let's say 5. Let's say my R0 value is 5. So I'm going to shift it, let's say 5 times. I'm going to shift it 5 times, or let's say 4 times. I'm going to say I'm going to perform now move R0 comma R0 LSL hash 4 I am going to perform. So what it is doing, it is going to shift this R0 4 bits and then it is loaded to R0 again. So always you know that whenever you perform a shift operation, it is nothing but we are actually multiplying the number by the power of the shift. Okay, so since it is 4 times, so I'm going to multiply the number 2 to the power of 4 times, that is actually 16. I'm going to multiply 5 into 16. That will be whatever the value come, that is a value in the R naught. So as you can see, it's a very simple technique. If you have says 5 is actually 0 1 0 1, and if you shift it one times to the left side, it becomes, let's say, 0 1 0 1. So this is one shift that I am doing. So I am actually equivalent to multiplied by 2. So this number is as good as multiplication by 2. So this 5 becomes now 10. So this is 5. So this is 5. And now it has become 10. Correct? So 2 into 5 into 2. 10 means A it is. In X number it is A. So if you shift it again, this becomes 1 0 1 0, and this is 0. What is this value? So this is again another value. This is actually 1632 plus 4, that is 36. Correct? So this is 32, this is 16, and this is 8. So now 32 plus 8 is 40. So this is now 40. So I'm going to shift it now 2 times, means 2 to the power of 2 is 4. Okay, so 2 to the power of 3. So this is actually, so one time shift, another time also shifting now. So this is as good as multiplied by, I'm going to shift it now 2 to the power of 3, that is 8 times. So 4 into 8 is 5 into 8 is 40. So that's how this is going to work. So every time you shift by 1, that power of 2, so this is again is multiplied by 2. So this is, here it is 10, and this becomes 40, and so on. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. I think here it is, yeah, sorry, I think yeah, this is actually 0 1 2, and this is 4. This is sorry, okay, I think I need to correct it once again. I'll take this, let me erase it, and I'll take it. So I'll repeat this again. Okay, so we have taken an example of shifting the numbers. Okay, so when you shift the numbers, it is as good as you are multiplying it by power of 2. That's what the statement is. So if you have a number here, so move R naught, R naught, LSL hash 4. Let's say I have this number. So this is nothing but it is as good as you multiply this number by 2 to the power of 4. Okay. So I have taken the number R naught as 5. So which is nothing but 0 1 0 1. So this is 5. Shifting 1 times to the left will lead it to 0 1 0 1 0. What is this number? This is actually 10. So how you, so this is the 2 to the power of 0 field. This is 2 to the power of 1. This is 2 to the power of 2. And this is going to be 2 to the power of 3. So this is 1, 2, this is 4, and this is going to be 8. So one time if you shift it, you as good as it is multiplying by 2. Third time when you shift it, it becomes 0 1 0 1. So how many shift we did? So this is here 1, this is again second time we shifted. So what is the value? So this is actually the 4, this is 8, correct, and this is going to be 16. So the number is actually 20 now. It becomes 20 here. So it is as good as multiplying. So when you perform a 2 shift, it is as good as multiplying 2 to the power of 2 times. When you multiply 3 shift, it's as good as multiplying by 2 to the power of 3. When you multiply by 4 shift, it is as good as multiplying by 2 to the power of 4. So we are actually performing a multiplication to the number, whatever the number is there, with that times 2 to the power of that many times. So here when we do something, it is as good as multiplying the r naught contents with 2 to the power of 7. So the barrel shifter has that functionality here. So it's a very powerful tool in the arm. They use barrel shifter to quickly get some numbers also. Sometimes they use it in some multiplication addition algorithm to get a better speed. Okay, so that is a usual case. If you look at the architecture here, that's very clear to you. See here, this is taken from straight away the architecture which I already shared. There is a register read. Okay, so in this we get the destination register here. This is our destination, and you may get our source here. So that source register, as I mentioned, there are two registers. The first operand straight away goes to the ALU. Second operand, you always go through a shift register. There is a shift register which moves here. So using the shift register, the value is goes to the ALU for the arithmetic operations. So how many times shift, that is indicated here. Okay, the value. So this will happen in the execution cycle. So whenever you go for execution of data with the move or add instruction, you can find three operands. Okay, three operands as you see the instructions. So this is actually two operands because it's a move. When you perform add, there will be three operands, two numbers to be added, one more is to be for the destination result. So here in the data transfer, two operands are there. So one operand is always loaded through the shift register to perform the required shift, and then it is moved to the destination register. So register to register data transfer, when you see a register to register data transfer, how it is going to work. So in the architecture level we can see here. So this was the same diagram which is taken from the architecture. There will be an address register. See, always this is actually the memory mapped here. This is memory mapped. So there is a memory map for the register. So this is register where you can address the registers R0 to R31. Totally 32 registers are there. Sorry, yeah, R15. Sorry, R15 registers. So R0 to R15, totally 16 register, but in different user modes, FIQ mode, IRQ mode, if you see, it will more than that. So R0 to R15, so that register, and that could be an auto increment kind of a thing, or it can be even the value of the PC that also comes sometimes. So eventually, if you see Rn and Rm, the two operands, okay, Rn and Rm, so these two are taken. So Rn is taken straight away as an instruction. This could be move something. So move what? Move this Rm to Rn. So that's what I wanted to move. Then the value will be saved back in the destination register, whichever. So you can take up the instructions what I have said already. If you say move R1, R2, if this is the instruction, so this R1 will come here, R2 will be here, and RD is nothing but R1 only. There is no change. So R1, R2 as an instruction, the value was saved in R1. So if I have an instruction move R1, R2, LSL hash 7, if I have something called as hash 4, then R1, R2, then there will be a shift of 2 position to the left. The new value will be loaded to R1. So that's how it happens. So this happens in the one cycle of execution. So this is how the data path activity is involved in case of some register operation like move instruction if you take, or maybe with the shift instruction you can consider. So these are all the data activities that are involved in this. So there is another case, register loading the immediate value. So whenever you load an immediate value, how the values are loaded. So when you load an immediate value, the immediate value is generally taken up by this shift operation if required. For example, I can have a specific an instruction to load an immediate value, say r3 comma, I can say r3 comma hash something, say 2, I say. So when you say 2, what happens value? It is always going to be a 32-bit number that is going to be loaded. Of course, shift can be of 8-bit shift you can provide here, not more than that according to this. Uh, so once you do this, now R3 comma 2 means, so here this is going to be the R3 and your destination also R3, and a number supposed to come from here, that is 2. That is something instruction pipeline supposed to give that number to you, this hash 2. So once you do that, then finally after execution you get R3 as 00000002. This is your 32-bit number. Okay, so remember always it's a 32-bit operating system here, or the 32-bit processor, so all the values are loaded 32-bit. If you have anything to be specified exactly, then you have to specify it here. And the ARM has a special feature of getting the immediate value by itself using this algorithm. Okay, so this plays, the barrel shifter plays a very important role in ARM processor. When you generate, for example, say I wanted to load a number, this is critical actually to understand. Say for example, I wanted to load a number r3 comma, let's say I want to load some number 45 66 77 and 88. Say this is the number that I want to load. So don't think that this number will come from here. What they do is they will prepare, and the architecture will actually design such that they will take one number, from that number they will generate this value actually. Why they are going to generate this value? You can save the, because your instruction is always 32-bit. Your instruction is always 32-bit actually, and they have to restrict this. Now if you can't handle it with only 32-bit now, because this number itself is 32-bit, then move r3 will take extra bit. So if you want to restrict this instruction within a 32-bit range, then they have to have a shift algorithm to get this number out. Okay, so they are going to generate this number. It is not in case of when you say 8051 how those values are saved. So you have an instruction move r2 comma hash 55. I'm talking about 8051 now. Okay, now if I say, then what happens in the memory? If you see in the memory, what happens, the opcode for this will be saved, opcode for this instruction will be saved, then in the next instruction opcode this 55 value will be saved. So that's what, this is something opcode for move r2 and next value. So ARM does not involve this kind of instruction format. They are, all the instructions are only 32-bit, that is fixed. It could have immediate anything, so that architecture will take care of it. So how this numbering, otherwise they will store this number in the memory in a lookup table, so there the PC comes into picture. Say for example, you have a number which cannot be generated at all, then what they do is they're going to save this number in the memory, okay, somewhere in the memory, and they will use this PC is here, so program counter is here. This PC will be used as a lookup table locator, and from the lookup table the value will be loaded. Okay, it may take an extra cycle, but instruction width will be always 32-bit. Okay, so this is involved in case of loading the immediate value. Okay, so another thing is data activity during the load and store instruction. So this I've already discussed, but how the activity is involved in the architecture level. So if you look at this example, so the data transfer instruction computes a memory address in a manner very similar way of data processing instruction. So first thing is to compute the memory address, either it to be load or store. You need to have the memory address. So that takes actually one cycle. After computing the memory address, then it this is going to load the value to the register or is going to store the value. So there are two phases involved in it. One is actually computing the memory address. That is again important. So computing the memory address, and another thing is load or store. So whatever it is, either it could be a load instruction or it could be a store instruction. So here I have given a load instruction where this R0 value will get it from R1, and this is a store instruction where R2 value will be loaded to R3. Okay, so that's a simple indexing. And there is one more, R3 comma address. Actually this uses a program user defined value in the memory itself as a lookup table. That value will be loaded to the R3. Okay, this will be using the program counter. So if you see how exactly the computation of addressing is done on the first phase of cycle. So there are two cycles involved, since it uses the pipelining. So in one phase it has to compute the address. In the next phase it has to read or write, because the architecture is such a way that it is based on the von Neumann architecture. So if you are using von Neumann architecture, then you know that the memory will be a single page, okay, or a multiple page or a single memory device where it is divided into different sections like program memory and data memory. Whereas if you go for Harvard architecture, then you find a different section for separate address and data line for the program memory and data bus. But since it's a von Neumann architecture, there is a common memory, that is the address bus is common for both. So you cannot use the same address bus resource at a time. It is not possible. That's why it is divided into two different cycles, as computing the address, next you're performing the read end. As you can see here, depending on the instruction, there is one register which will be loaded to the ALU, and other could be an offset also. See, again offset can involve your LSL register, barrel shifter also going to be there to generate the offset. Once the offset is prepared, that is actually given back to the address register where you actually handle. This is actually connected to the memory. So here it will connect to the memory. Okay, so this will be addressing to the memory. So these are the base and offset registers value. This could be a base and this could be some offset. So I can specify, let's say move or say str or ldr. If I take an ldr instruction, ldr r3, then you can specify r1 plus something, r1 plus something as 3. Then 3 is offset here, and this is going to be the r1 and 3. So it's going to perform that addition, subtraction, or whatever you suggest. It's going to be perform that, and then it's going to load it to the register. So now again there is a shift which is having a limited instruction. So once you get that offset, then the next is actually the data transfer. So this involves, so this computation is in the first cycle. This is going to happen in the first cycle. So you perform this in the first cycle. The second cycle of the instruction, we going to store the data. Okay, either maybe in the memory or from the memory to a register. So here if you see, now whatever the values taken up from the memory addressing, so we are going to use it uh, here for the storage. So first thing, if you see here, the destination register is used. So if you look at this, so here the value which is taken from the destination, now it is going to move to a data bus. From there it is going to the location, either it could be a memory. So say there are the store can happen either, so if it could be to a memory or it from a memory. Okay, this could be a register, and this is register, and this is memory. So I can have some register to memory or memory to register. So in case if it is a register to memory, okay, register to memory, then here is always addressing is done. The destination will go to this byte, and from this byte will go to the data bus. So this will go to the data bus. Okay, data. So here it goes. If it is from memory to then what way it will come? So this, the value will come to this byte. From the byte the value will be loaded to the registers, whichever the register we are addressing. So this is how the store data can be made either in the second cycle. So this happens in the second cycle. So whenever you have ldr instruction, ldr instruction, say r2 comma r1, then this will take one cycle, this will take another cycle. Okay, so these two are two cycles because of the architecture issues. Okay, so that's how the store operation is performed. So these are the two things, these are the main things that I wanted to discuss here: the store and the how the data path activity is involved. There is another topic which is on the branch instructions, which I'll be covering it later. So thank you.